Hello, everyone. Welcome to the Nomads Podcast. I'm your co host, Bhavya.
And I'm your co host, Prachi.
Recently, I came across a definition of a good theory. It should explain as much as possible, with as few ingredients as possible, and with as much accuracy as possible. And I think this is something every serious physicist can relate to. And honestly, this is what modern theoretical physics is striving for. In one way or another, physicists are trying to push boundaries of what makes up a good theory. They do it by not just identifying what the universe is made of, but also understanding the mathematical framework that makes the laws of nature hold together. Now, arguably, the most remarkable theory that theoretical physicists have come up with is quantum field theory. And believe it or not, we do not fully understand the mathematical foundations of the theory. We're looking for hidden structures and patterns behind forces, symmetry, and space-time itself. And it opens up surprising connections to geometry, topology, information, and mathematical logic. Our guest today, Piotr Sułkowski, is precisely exploring these kind of frontiers of modern theoretical physics. Through research spanning string theory, gauge theory, Seiberg Witten theory, matrix models, quantum curves, knot theory, and even biophysics through the topology of biomolecules. Piotr is a professor of theoretical physics, the chair of quantum mathematical physics at the University of Warsaw in Poland. Alongside his research, he has also been actively involved in making science accessible to broader audiences through outreach projects like Ask a Physicist at the University of Warsaw. So if you're interested in exploring the mathematical foundations of theories of physics, you're in for a treat. Let's go. Piotr Sułkowski, welcome to the Nomads Podcast.
Yeah. Hello, how are you?
So let me start by thanking you, first of all, for organizing this school on integrability, complexity, and quantum chaos here at University of Warsaw in Poland. And I must say that the entire organization committee and the speakers did a fantastic job. So thank you for that. So to begin with, I know that you have a wide range of interests in physics. Sometimes they go beyond physics and mathematics to other areas that we will also talk about in some time. But particularly your focus and interest is more on formal aspects of string theory, quantum field theory, knot theory, and so
That's
on.
right.
And because a lot of your work is very highly mathematical, we'll try to keep it fairly general, try to get the gist and understand what are some of the open problems and how it all connects to the bigger picture and so on. So let us jump right in. Talk to us about what quantum field theory is. We know that quantum field theory is the best candidate theory that we have that explains everything around us to remarkable accuracies. So how do you think about quantum field theory? What are some of the inconsistencies that actually drew you to think about formal aspects of quantum field theory? And what exactly are you working on?
Yeah, so the problem is not just mine, but I think many people say that we don't quite know what quantum field theory is. We have different sets of tools for different problems to do different theories, but there is no proper mathematical formulation in general of quantum field theory. So of course there are these examples where we can measure some things to incredible accuracy, and when you say incredible accuracy, it typically means that you make some perturbative expansion and then you can compute various corrections theoretically in some coupling constant which is small. You can measure that. But the problem is what happens when this coupling constant is getting larger, and how to formulate such examples. So kind of general goal of my research is to try to find such general formulation of quantum field theory. What is also known, there are many examples for that there are so-called dualities or equivalences between different quantum field theories. it turns out that completely different formulation of the same problem or physical systems is like mathematically equivalent to some other formulation. There are examples where some theories with small coupling in this sense are claimed to be equivalent to some other formulation where some coupling is large. So such phenomena should be a part of our understanding of what quantum field theory is. So we would like to have such a broad picture, not just ability to compute some corrections and then comparing with experiments, but more general understanding.
So why in this particular regime it becomes hard to do quantum field theory?
Well, with coupling constant becomes large, then you cannot make this perturbative expansion because other terms that you would compute would be in fact larger. And larger, so they would not converge. So that's the main difficulty, how to deal with such things. Well, on the kind of practical level, but on the conceptual, you would like to understand what are some basic equations that describe our world, and you would like to have general understanding of them.
So is finding like a duality, is that the only way to address this problem, or is there other ways to get exact analytical results?
Well, there are different approaches. So one, you also mentioned that I'm also interested in some aspects of string theory, which turns out to be, at least in some cases, completion of quantum field theory or some generalization of that, and especially if you have supersymmetric theories, some of them maybe more special one, but they are just inherently related to string theory, and somehow you cannot pretend that string theory is not behind it. They are at this moment not describing immediately the phenomena which we really observe in nature, but conceptually as examples of quantum field theory, they are very closely related to string theory. So then you should like to understand the whole picture, including the string theory as well as natural generalization. And then often string theory gives you also some means of making maybe precise computations or finding some exact results.
I see.
So perhaps this non-perturbative problems we see in many of the different fields. Like this is one of the fields that is one of the problems that is common to a lot of fields with open problems. Do you think this non-perturbative aspect will come up, like we will have some sort of analytical grasp for this non-perturbative aspects that we see everywhere?
Well, there are different phenomena with different specific ways how this non-perturbativity appears. My hope is that we will have, but of course I cannot say precisely how. Maybe it's not even that that's important to be able to compute something exactly, but also have understanding how to think of some system, some conceptual view of that, even if you maybe cannot compute something very precisely, but still know the equations which describe a system, even if you cannot maybe solve them.
Right. So one of the many, like in theoretical physics, geometry plays like a very crucial role. Whether it's apparent or underlying geometry. However, in quantum physics, this geometry plays a very different role. And one of the things that you study are called quantum curves. So how about you explain what are quantum curves?
Well, it's hard to explain very quickly, but just for general audience, by curve here, it may be a bit misleading when you hear a word curve. Probably you think of something like a line. I hope I'm seen in the camera, so I mean like a infinitely thin line in space. This is what comes to your mind. But in the context of research I'm doing, we think of these curves as being curved in complex space. So just complex means that it has two dimensions, not one dimension. So it's more like a piece of sheet of paper bent in some way. So there are some problems where certain so-called observables in quantum physics, things that you might in principle measure, they are encoded in the classical limit in this kind of curve. So this is like two-dimensional surface. And then it turns out that the same problem, when it is considered on a quantum level, then observables that you measure in that context in quantum world would be encoded in the object, which is quantization of this curve. So it's not just a smooth surface, so to say, but it is quantized, so you may think of it as being non-commutative. So as we know in quantum mechanics, coordinates or various observables are not commutative. It may also happen just with coordinates on the surface, like there is, instead of x and y, which you cannot multiply in arbitrary order, it turns out that if you multiply x by y, it is something different than when you multiply y by x. So in that sense, the surface may be non-commutative, or a curve in this two-dimensional sense. And such a curve in some way captures certain things that you would like to measure or compute in a given system. It's hard to me to very quickly give examples of such systems, but these are some quantum mechanical systems, maybe like a toy models that we consider to try to understand how information about quantum amplitudes could be assembled or maybe have some more general structure that is not immediately seen.
And it is smooth in certain limit.
You can take so-called classical limit where you forget about this non-commutativity. And
Right.
These coordinates become commutative, and then you just get a smooth curve or like Riemann surface, so like a donut or something more general with some number of holes.
I see. And much of your work has also been on knot theory. So what are these knots, and how does one think about these knots in physics?
Yeah, that's a nice question and nice area. So by knots, we just mean knots that you have in mind when you say word knot. You have a piece of a string and you entangle it somehow. So what is important that when there is a branch of mathematics called knot theory, when mathematicians consider knots, they would like to have them uniquely defined. So to have uniquely defined knot, if you have something on like a tangled piece of a rope, you have to connect ends together so that you cannot disentangle this without cutting.
Right.
And then you can move parts of those strands in some way, but it is still preserves a type, so-called type of a knot. It is called topological type of a knot. This knot theory is a subfield, you may say, of topology. So then for mathematicians in knot theory, the main problem is how to recognize what knot you have. If you have two different entangled pieces of rope, can you transform one to the other without cutting, just by moving strands, but without cutting them? And this is a very non-trivial problem. And one way to address that is to compute so-called knot invariants. So these are certain mathematical objects, either just numbers or maybe some functions or polynomials or more complicated objects, which you can compute if you have some configuration of some knot. And then there are theorems which tell you that if you have two such knotted configurations, if you compute such invariants of the same time for one and the other, if they turn out to be different, it means that these knots are not topologically equivalent.
I see.
So this is what mathematicians do with knot theory, and then what this branch of physics, which is related, which I am also interested in, deals with also some quantum theories which have topological invariance, which means that certain observables, things you would like to compute or measure in those theories, don't depend on precise geometric shapes of different objects involved, but just of topological type, like in the spirit of knots, that you can move something, but if you don't cut it, you get the same invariance. And then you can devise such a theories where also such knotted configurations appear. They are called Wilson loops. And if you compute expectation values, amplitudes for these loops, they turn out to be equal to knot invariants that mathematicians consider.
I see.
So this gives you physical viewpoint on this knot theory, and then this is useful for both fields. So from physics you may get some insights how you think about knots, how to construct new knot invariants, or from mathematics you can use some results which tell you about some quantum amplitudes. So this is very interesting.
And
the
along with, I
area.
think, some of your collaborators, you, again, talking about dualities, you coined, came up with the knot-quiver correspondence.
Yeah, so this
So
is
what are quivers and what's this correspondence?
okay. Quiver is also something simple. This is just a graph which consists of nodes or vertices. So we have a bunch of nodes, and then they are connected by arrows.
Okay.
So this is just example of a graph, like you may say, oriented graph in a sense that there are links between the nodes, but they are oriented, so there are some arrows. So what we found is that if you have some knot, and you can compute various types of invariants for this knot, then you may also find the same invariants if you consider some quiver. It may at this moment sound very abstract, but you may find some quiver which is associated to a knot, and there are also mathematical characteristics of quivers, some also type of invariants which you compute, and they tell you something about the structure of this quiver. And they turn out to be the same as invariants of this corresponding knot.
Right.
So for mathematicians, this is like connection between two areas of mathematics. There is this area, people working on quivers, this is called quiver representation theory, and so far until recently it was completely disconnected from knot theory, but thanks to what we found, now people see the relations between two branches of mathematics, but in fact all this has physical interpretation in a sense that this observables that I mentioned related to knots, these are some amplitudes in some specific quantum field theory. And this quiver also encodes some other quantum field theory. So for us physicists, this relation between knots and quivers in fact is a knot between these two different quantum field theories. This is some example of a duality. And moreover, it can be also kind of derived in a physics sense in such a way that it follows from some relation between two versions of string theory.
Right.
I see.
Okay.
So you can in some way embed these two systems in string theory, and then there is in fact some geometric transformation which relates one string theory to another, and these two versions of string theory can be described also by these two quantum field theories.
Interesting.
Right. And before the concept of these correspondence, there was no way to find any relation between these two different quantum field theories.
Well, they were just not considered.
Right, okay.
They didn't seem of such an interest for people to just think that there might be connection between them. And also for mathematicians, there were no known connections between some aspects of knot theory and the quiver representation theory. So this is some activity in recent years which some people are now looking at.
So as far as I've read about it, on the quiver side, we talk about things like BPS states, or when we talk about string theory, we talk about branes on the quiver side. How do we physically understand what happens in the knot side?
So both these things are, it's maybe more clear when you have the string theory picture.
Okay.
And this is often the case, that if you embed some things in string theory or M theory, then it gives you some intuitions which are maybe not immediate just from the viewpoint of quantum field theory. So that's one reason why it is useful. And so in the string theory, the point is that you have to consider objects which are called branes. So these are some higher dimensional objects. And what you consider is, first of all, some kind of geometric setup in which you have a part of this setup is three-dimensional sphere. So I should also make a side remark that when we think of usual knots, they are embedded in the three-dimensional space. So you might think that this is just three-dimensional, like R3. But this is equivalent to considering knots in three-dimensional sphere.
Okay.
S3. So instead of R3, you can equivalently up to some minor subtleties which we may ignore. Think of a knot in S3. That's also three-dimensional space and something knotted there. So people construct some specific geometric setup, string theory in a sense, in a space-time, which has a part of that is this free sphere S3, and the rest of the space-time is in some way trivial. And then what you do, you consider this extra brane, which for some reason has to be, it has some number of dimensions, doesn't matter, but what is important that it intersects this three-dimensional sphere along one-dimensional curve.
Okay.
So this one-dimensional curve represents this knot we want to analyze.
I see.
And then in one setup, this is just equivalent, this string theory setup, this is equivalent to this topological string theory that I mentioned before. And specific example of that is which is called Chern-Simons theory. And then the string theory amplitudes in the system are equal to this amplitudes in Chern-Simons theory.
I see.
So that's one side of this story. And then to go to a quiver, you make a transformation. So such transformations or transitions are considered in string theory, which is related to some singularity in space-time. Namely, you take the size of this free sphere, you shrink it just so that it vanishes to a point. So it's like going to singular point, but because this Chern-Simons theory related to that is topological, it doesn't matter if something is small or big, then amplitudes are the same. But you can shrink it to this to be of size 0, and then this, so you get kind of so-called singularity, and then you can again deform it in some way so that get rid of singularity, have some smooth geometry, but you can do that in some other way, where instead of this three-dimensional sphere, you get two-dimensional also sphere S2. Their overall geometry has the same number of dimensions. In string theory, this is 10, so overall geometry is still 10-dimensional. But you may deform the singularity in different way, or in two different ways, either with this S3 or with two-dimensional sphere S2. Right. And then in this second type of deformation, this brane that I mentioned in the beginning existed there and encoded a knot in this S3. It still exists after this transition. And then on some other part of this brane, you get also description of the system with this S2 in terms of some supersymmetric theory, supersymmetric gauge theory. So this is not like this initial Chern-Simons theory, this is some other theory, but this resulting theory is equivalent to this initial one in a sense that some observables you compute there are the same to this initial one, so they also encode some not invariants.
I see.
And then the structure of this theory, this last one that I have in mind, can be described by a quiver. So that is physical system. The quiver captures some states which exist in this sphere, and the arrows in a quiver capture interactions between the states in some way. So I can't go into too much details without becoming very technical, but what I want to stress is that these objects, they have some physical meaning and encode some physical properties.
Would you say that this physical meaning has been better understood after we have this correspondence?
Physical meaning of those objects was known before, either for this sphere or for the other, but now we see that they are, as we say, dual to each other, and they encode the same quantities, so that's a novelty.
Right, okay.
Interesting. So like, again, maybe a slightly naive question. This topological string theory, where does it fit in this whole string theory picture? I mean, what how does this
topological string theory?
Yeah, how does it become? How does topology become manifest in
when we say topological string theory, it means that some observables that we compute have some topological invariance, which means that if we deform a part of us, either the string theory space-time or some objects embedded in that, like this Wilson loops, then the amplitudes, quantum amplitudes, don't change if we deform them. So this is the meaning of the word topological. And then it turns out that these topological amplitudes, they compute some subset of amplitudes in like the full non-topological string theory. So this is also one reason why people consider this topological string theory, because they compute some specific sector of the full string theory.
Right. I see. Yeah,
So should we just consider topological string theory as like a computational tool, or What do you say?
No, I wouldn't say so. For me, it's more interesting to think of it as a maybe toy model, but for this
Okay.
kind of dualities, to have some conceptual understanding
Interesting.
how different theories may be equivalent to each other. So not just the final result of computation is important, but rather this type of processes that I describe with the singularities going through singularities. Maybe it's quite far from singularities we can observe in the sky, but still maybe the first steps to have some idea
Get a toy model working and then...
what may happen in such singular
makes sense.
space-time. So.
Right.
And do you think topological string theory helps in other aspects? Like, does it help in constraining the string theory swarm plant?
Well, I shouldn't maybe say too much on that. I'm not working on some plants, so
Okay.
there are some links indeed, but I'm not that expert on that
Okay.
topic, and also not maybe up to date with last results.
Totally fair. Okay, so maybe zooming out a little bit and talking about ongoing experiments and so on. Do you think there's like any experiments that you're having a close eye on that maybe help you constrain and understand and more of this duality, let's say?
Not
Not really?
myself. There are indeed some links between experiments and some ideas coming also from string theory, maybe more of them even recently in condensed matter, in different phases
Right.
of matter and so on, but it's not what I'm directly working on. So I have more links with mathematics, I would say, than with
Right.
experiments in my research.
Because you
At
mentioned Chern-Simons and that it is, I mean, it's realized in condensed matter systems.
Yeah,
and
that's
so on.
right. That's right, but not immediately related to
Okay.
what I do.
So again, moving beyond your interest in physics and mathematics, you and your wife Joanna, I think, work on protein structures and folding, and using principles of knot theory. So what's the connection here? Like, how are these two things connected?
Yeah, they are simply connected.
Simply connected. I see.
In a sense that you said this word proteins. So indeed, what my wife did, this is how our collaboration started. She works on the problem called protein folding. So the problem now, people claim it is solved also because of AI, artificial intelligence.
I was going to ask about that. Yeah, but go on.
Anyway, the problem is such that when proteins are being formed, they consist of amino acids. So each protein is a long chain of amino acids. It can be several hundred or even more of amino acids, which are attached one by one when in the process of formation. And then to function in some organism, the protein has to, as it is fold. There is this folding process, so it has to take some specific three-dimensional shape to be able to do something it is supposed to do. So you have like a chain of amino acids. If you forget about amino acids, it's like a chain of letters, so to say. And from that chain of letters, you would like to predict what will be the three-dimensional structure of a protein.
Mm-hmm.
And then if you have like long chain in our three-dimensional space and it folds, then you might expect that it forms a knot as well. It might be, it might not fold a knot, but if you have like telephone cable or any other cable, it's quite often entangled randomly if you keep it in a bucket. So
Right.
we know that well. So for a long time, people thought that it is impossible to have knotted proteins because it's too complicated to form a knot for some reasons. But then it turned out that such structures exist, and this is what we started looking at.
Interesting.
So my wife had experience with proteins, and I had this input from knot theory, and that's why we could combine
I see.
forces. And now it is known that quite a few, well, people say 1 or maybe 2% of proteins are knotted, but in absolute numbers, these are still large numbers. So people want to understand why these knots exist, how the evolution made them created, and how what functions they may play. If this is quite complicated still to make such a knot, then it should have some non-trivial functions, and so that it is indeed in nature. Otherwise, it wouldn't probably exist. So that's kind of a subfield of this protein.
Interesting. Are other people working on this?
Yeah. This is now very active.
Oh, very active. I see.
Area of research, and also experimentally, people want to see manifestations of the existence of knots. Also, there are some hopes that they may have applications in medicine, because these knots are related to functions of some proteins, and if they don't work properly, then something in your organism might not work properly, or you might use that to whatever, transport some medicines to specific places in organism, people think of even such medical it's of course probably far away, but you have to start somewhere.
So from the knot side of things, do you only let's say get constraints on these structures, or do you also can predict how these chains of amino acid can fold in 3D space?
Well, this is one of the puzzles in protein folding, to predict whether from a given sequence of amino acids you will get some configuration which is not it. The first thing you are doing is just classify existing protein structures and determine whether they are not it or not. And even this is very complicated task, because if, as I mentioned, this protein has several hundred amino acids or even more, then by naked eye you cannot see whether it is knotted or what type of knot it is. So you need to use some mathematical tools, in particular this knot invariants I mentioned before. So they appear also here. So whatever it is, high energy physics or some abstract Chern-Simons sphere, or here real protein structures, use the same knot invariants to determine what knot you have. And still this requires a lot of, in fact, brute force, so to say, on computational power, because for one protein you have very long chain, so it is hard to analyze it and tell you which knot it is. And then if you have now from this AI, millions of structures are predicted, I mean they're three-dimensional shapes. Or there is some a bit older database with structures which are known from crystallography, or so there are also several hundred thousands structures. So to scan all of them and decide whether it is knotted or not, you need a lot. You cannot do this just by hand and looking at each picture if you have millions of structures. So this requires more computing power, but also some good mathematical algorithms which simplify this computation so that they can be done in finite time.
Interesting. Now, let's getting a little philosophical. As someone who works in string theory, who's a candidate for quantum gravity, do you also think about quantum foundations? Do you have a favorite interpretation of quantum mechanics?
Not on an everyday basis.
You sometimes think about it?
Well, sometimes, but I'm not going that much into details. It's not immediately. Maybe I'm somehow building up on these formalisms that we already have, also computational ones. So I don't need to consider different interpretations of quantum mechanics for the kinds of problems that I work on, like these different dualities between different theories. I don't need to think of what quantum mechanic interpretation stands behind that.
In this theoretical physics community, this usually goes by the shut up and calculate sort of subscription, which is...
Well, I wouldn't say calculate. We have kind of a bit different approach. As I said, we want to conceptually understand relation between different quantum field theories. We don't necessarily have to just calculate and compare.
Okay.
But like in this example with this singularity, we have some geometric structure of space-time, and it can be deformed in some different ways, and this corresponds to the different field theories standing behind that. So we often would like to have such geometric interpretation of different processes. So it's not just the result of calculation and some number which you compare at the end.
So do you think people should actively work in understanding the foundations of quantum mechanics?
Yeah, of course, they should work, and it's also connected to some issues people consider in string theory. It's just not that I need it immediately to my work and think of that every day, but of course we should hopefully one day have some final viewpoint. If there are different interpretations, but people still argue which is correct, it means that there should be some answer. So of course we should find it, but it's maybe too complicated, and I'm not sure if it helps if all physicists work just on that and every day think of one of these interpretations. There are many questions and things we have to look at. So.
That's very well put, actually. So we can now actually move on to the very end of the podcast, and on this podcast we really love to highlight people, especially physicists from different background, and highlight their journeys and so on. So briefly tell us about your journey in physics, how you grew up, and how do you develop this interest in physics?
Well, I don't know how it just developed itself in a
Okay.
sense. I was as always interested in physics. So when I was like in high school, I don't know, my father had some old textbook in physics. He was not a physicist, but he studied some engineering or so, and I had maybe some lecture course in the basics of physics. So I like to look at this textbook and see what it's about, and also read some popular science books like by Hawking or whatever, Michio Kaku and such things.
Yeah, of course. Yeah, okay.
And yeah, then I decided I would like to study physics. And I didn't have any better and other ideas than continuing
In
like
physics.
PhD student after that. So I went to for PhD, and then I made connection with people in Amsterdam. So the things I was interested in, like this topological string theory, for example, people didn't work on it that much in my department.
Mm-hmm.
But there was very strong group in University of Amsterdam, and I managed to make connection with them. Then I got a co-advisor there, and for 3 years I was commuting between Warsaw and Amsterdam and
Oh, interesting.
during my
I see.
PhD. And then I went for a postdoc. I also didn't have any better ideas what to do. So I spent 2 years in Germany, in Bonn, and then a few years at Caltech in US. I was also shortly in between at Harvard. And then after that, I got a position here at University of Warsaw.
I see. I see.
I also spent almost a year in Amsterdam, still in the meantime, but I already had position here, and then I came back, and
Interesting.
since then I'm here.
So we also share, by the way, some of our alma mater. I think you were in Durham University.
Oh, that's right.
We did our masters from Durham as well.
Oh, great.
Yeah.
Yeah. So when I was master student, I spent half a year in Durham in some master course.
I see. I
There's
see.
a certain Center for Particle Theory.
Yeah, CPT.
And
Yeah,
they
that's where
have-
we were as well.
Oh, great. Great to hear.
So you've also been very active in science communication. What are your thoughts in science communication? Do you feel that all physicists should actively participate in some sort of science communication?
Not necessarily all, but I think some representative number of physicists, so that if some people want to hear something and learn about, they should not have difficulty. And what I think is very important is also direct personal contact. So not just looking at some movies or even interviews, but having an opportunity to go to a lecture, to some event where you can talk face to face, and there should be enough number of physicists so that at least within whatever some distance, a number of miles from where you are, you have a chance to attend such a meeting.
Right. So, like, personally, what are some of the things that you do as a science communicator?
Yeah, so the main thing I do has been already for many years, like a bit more than 10, is some activity that we call Ask a Physicist.
Oh, interesting.
It's
Okay.
associated to our department, but I'm responsible for that. And we have two main sub-activities of that. One is public lectures that are organized every month or maybe 2 months during the year. So usually we have 7 or 8 such lectures, not in summer during holiday time, but for the rest of the year. And some prominent physicists also, and
Interesting.
people who popularize science give lectures, mainly in physics, but also on the border. Sometimes it's border of physics and chemistry, or biology, or physics and math. So even some Nobel Prize winners were here.
Oh, nice.
Roger Penrose, for example, gave
Right.
one of these lectures, and also Marina Wiazowska, she got Fields Medal in mathematics. So
Yeah,
this is
yeah.
the most important prize. People say in math
In
there is
math,
no
yeah.
Nobel Prize, but it's that prize. So she gave one of these talks. So well, this year we had the 10th anniversary of these lectures.
Oh, wow.
So we had
I
also
see.
some special events, some special
That's
discussion
brilliant.
on the 10 years of that, and it's been like above 70 or almost 80 lectures and during that time. So that's one activity, and another one, well, these lectures are also announced in some portal that we have, and in the same portal we answer to the questions that people can send us. So we have some questionnaire, and people can formulate some question related to physics, and then I coordinate some team of people in our department, scientists and also some students, who write answers to such questions, and then we post them. So we have also like 1,500, I think, answers
Mhm.
on this portal, and we update it. Try to do this regularly. So these are these two activities within this Ask a Physicist. So this is already taking some time. So I also try to be active in some other ways sometimes. Sometimes I write some maybe a piece of popular text or
Okay.
Oh, that's very nice. Yeah.
participate in some other event, but this is the main thing I'm doing. And
That's very interesting. No.
so this lecture you mentioned, the school we had last week, it was like a school for physicists. It was advanced school, so for at least PhD students or older ones. But one evening during this lecture, we had public lecture. It was a lecture in that school, but at the same time, it was a lecture in this series.
Right,
I
right.
coordinate, so it was part of that as well. And then we have also some YouTube channel with all these lectures.
Oh, these public lectures are recorded?
Yeah, they are recorded,
Okay,
and so
Oh, that's
some of
awesome.
them are in English, as I say.
Oh, great. Yeah, last one.
If there is the last one, or if there are speakers from abroad, they of course speak English. So there is this lecture by Penrose and
Yeah. Oh,
others.
nice.
So if
Nice.
you're interested, I can then give you details where to find it. And
Yeah, we will make sure that we put all these details in the video. The last one was by Tomasz Prozan, who was also one of the lecturers.
yes.
I see.
Brilliant. And finally, what would your advice be to young researchers all around the world?
Well, I would advise just to do what you find interesting and what is of interest to you. I believe that if you do that and follow what you really like, then at some point you find your way. So you shouldn't think that this is more profitable or maybe politically correct to do this or that, and you have more chances to get a job later. But just if you know what is of most interest to you, just try to focus on that and do your best.
Very interesting.
To
On
develop
that
it.
note, Piotr, thank you very much for being part of the Nomads podcast. It was a pleasure having you.
Okay, thank you very much.
Thank you.